Okay, so I want to continue on with this serverless stuff. Now, we've looked at Lambda and DynamoDB, and I want to look at one other service as well called API Gateway. But I actually want to go back to the Lambda stuff because we've skipped over some slides that I'd like to cover with you. So if we fast forward through these. This is about roughly where we finished off the last day. So it turns out that a Lambda function on its own, it can't really do anything in terms of interacting with other services unless it has the permissions to do so. And that means that's where IAM, the Identity and Access Management Service, comes in. So there are two parts to a Lambda function in terms of its IAM permissions. One is what the Lambda can talk to or communicate with, and the other one is who can communicate with the Lambda. So the execution role is that controls what a Lambda service can do in terms of communicating with other services. And as we know from what little you know about IAM from last year, IAM is all about roles and policies. So uh, each each Lambda function has an IAM role attached to it, and then the policies determine the policies associated with that role determine what the Lambda can do. Now, there are some predefined policies, kind of convenience ones that I'm listing some of them there on the slide. But of course, you can create your own IAM policies. Um, Now, where that comes into play in terms of the CDK, if we look at the CDK code for essentially for the lab that you've been working on so far, which is this here, right? So you might remember now we have a Lambda. Let's see, which one am I interested in? It's this Lambda here. This is the Lambda that talks to DynamoDB to get movie items. So that's fine. And then further on in the CDK stack, I have statements like, where are they? Am I looking at the right one? Yeah. So statements like this one here. And as we know, what that does is, in this particular example, it gives this Lambda function, which is the one we're actually interested in, it gives it read permission to this table. Now, when we CDK deploy this stack, the effect of that single statement is as follows. So if we go into the Lambda service, and find the Lambda function that we're interested in, which is this one here. And then if we go into the configuration section and the permissions section, then here we have the execution role part. So there's a role, an IAM role that was created, and this was created by CloudFormation for us, even though we didn't have any direct code in our CDK stack for that. That's one of the benefits of the CDK. There are some kind of defaults that are automatically happen. So this IAM role was created and was attached to our Lambda function. And if we drill down into it, we switched over now to the IAM service. We can see that there are two IAM policies associated with the role. The first one is one of these managed policies. If I jump back to my slides, these managed policies are predefined policies. Now, this one here, this is automatically attached to every execution role of a Lambda. And essentially what it allows the Lambda to do is to talk to CloudWatch logs. So by default, any Lambda will have that policy attached to it. But the second policy, it was actually created as a result of that single line in the stat file that I highlighted, this line here. And to prove that, in a way, if we look at the actual policy, and you're familiar with IAM policies to a degree anyway from the automated cloud services last year, you can see that the policy is all about essentially what I've highlighted here are endpoints of the web API that's wrapped around the DynamoDB service. Remember, we said that every AWS service has a web API interface, and like every web API, it has endpoints. Well, here what we're listing are the particular endpoints that we are allowing. Where do we say allow? Do we say in the policy? Yeah, the action is, well, by default, it's allow. It should say allow. Oh, there it is there. We're allowing all of these endpoints to be essentially kind of used by our Lambda function. Now, as it turns out, we know that the Lambda, all it does is it tries to read an item from the table. So some of the permissions that were granted, it doesn't really need. So arguably it's kind of over provisioned. But that's okay. They're still all just read operations. There's no write operation in this list here. So anyway, that single statement in our CDK stack had the effect of creating this policy, attaching the policy to the role, and thus allowing our Lambda to work properly. If we do a simple test, if I comment out this line, actually, no, I won't do that. I won't do it for now. I did say there that, like, arguably, it's kind of over provisioned. So we could, if we wanted to, and in general, we can write our own IAM policies in our CDK stack file. We don't have to use the kind of built-in ones. And so just to illustrate that, what I'm going to do is I'm going to enable this code here. So you can just get a look at what it's like to create an IAM policy for a Lambda and attach it to a Lambda. And so here we go. This is the Lambda function. So there's this add to role method. And here we're creating a new IAM policy and et cetera, et cetera. And the structure of this, really what I did was I essentially grabbed or copied all of this and pasted it in because it's structurally it's JSON really stroke JavaScript. So it's just convenience really. And you can see in terms of the actions, the only action that I'm allowing is this one here. I've left the others in there just for illustration purposes, but the only one that's active is that one. So if I now comment out this line And now I am customizing my IAM policy for the same Lambda. And if I do CDK deploy, and let that take effect, and then we'll look at what doesn't it like. Do I have an error? I do somewhere. Oh yeah, I need to comment that as well. So what I should see now when it's fully deployed is the IAM policy will just have one action, which is this one here. And the Lambda will still work, hopefully. So we'll try and trigger it from Postman, and it should still be able to read a movie from the movies table. Hopefully it doesn't take too long to deploy. Okay, so it has deployed. Let's go back to the management console. And let's refresh. Let's refresh this, I guess. And now if we look at this policy, you can see that it's much slimmer, and the only action is the one that I coded in my CDK stack file. So the overall point of the illustration is well, a couple of points really. The idea of this execution role, and also the fact that we can actually write our own IAM policies, not just DynamoDB related IAM policies, but any IAM policy if we have specific needs or custom needs that aren't handled by a nice kind of convenience function in the CDK code. If we didn't have, if we go back to here, typical kind of mistake that we make, let's undo all of those changes actually. A kind of common kind of mistake that we might make when we're developing code like this is to forget to give the necessary permissions. So if I comment out this line, and my custom policy is commented out now as well, and if I deploy again, so now my Lambda doesn't have any permissions to talk to DynamoDB. No, I guess I should have tested the custom IAM policies, but you can take it from me that the custom policy worked as well. But now we've disabled all access, all DynamoDB access anyway for the Lambda. So that means when we trigger it, it shouldn't work. Okay, let's just check the execution role again. No, okay, so it only has one policy now. That's the one that allows it to talk to CloudWatch logs. So now if we try and trigger the Lambda, so the Lambda actually has a URL which I've already uh, configured in my Postman, and the URL is this one here. So if I try and do a get specific movie, try and get movie 1234, I get an exception, and it's this access denied exception. And access denied is, it's generic in the sense that it's telling us that our Lambda is trying to access another service and it's denied permissions to do that. If we looked at the detail here, we'd probably work out that it's DynamoDB it's trying to access. Also, so this exception that you're seeing here, that was essentially thrown by the Lambda. I had a try catch block in the Lambda, and the catch block just essentially just caught the exception and rethrew it. So eventually what happens is the Lambda function returns to the Lambda service, and the Lambda service returns back to the client in this case being Postman. And in this case, the response back is our actual exception. But if we looked at the log for the log stream for the Lambda function, so if we go into CloudWatch logs, and this is the log stream or the log group. This is the log stream. Now, there's only one stream, so we invoked it once. We only invoked it once actually. So, and if we look down through the log stream to, let's say here, there's the actual exception appearing in my log stream, and that's what was returned back to the client. So this, as again, as I said, access denied exception always, nearly always means you haven't given your Lambda function the necessary permissions to talk to whatever service it's trying to talk to. Okay, that's that. That's the execution role. Then there's this thing called the resource-based policy, and resource-based policy controls who can trigger, who or what can trigger your Lambda. And by what we simply mean what other AWS services can be the source of the event that triggers your Lambda. So you either configure that at the Lambda level, and if you do, it's under the resource-based policy, or you configure it at the source side. Yeah. Um, Also, you would use the resource-based policy to allow other AWS accounts to trigger your Lambda. Uh, so that's kind of what we're saying here. That's what the resource-based policy is all about. One illustration of that, if we go back to the same Lambda that we're looking at, the Lambda that we're looking at, if we look at the code again, sorry, it has a URL associated with it. So let's pick out the Lambda again. Yeah, so there's the Lambda, and you can see here I'm also attaching a URL to that Lambda, or I'm getting the Lambda service to generate a URL for it. Now, it turns out that that URL, you won't be able to use the URL to trigger the Lambda unless the resource-based policy of the Lambda actually allows it. And so to prove that to you, so by virtue of the fact that I have this code in my stack, that actually caused CDK and CloudFormation to generate a resource-based policy for my Lambda. So let's just look at that. Let's see, which one is it? It's that one. Into configuration again, permissions again. And here's the resource-based policy part. Now, there's actually two parts to it in this case anyway. Which one is it? I think if we look at this one, kind of the way you interpret this is we're allowing any principal. A principal in this case could be another service or another IAM account, but because we've set principal to star, then that essentially means any other service or AWS account. This policy applies to it. And what is it about? It's about allowing that principal to essentially use the URL and to invoke my Lambda via the URL. Sorry, I'm looking at the wrong one. Sorry, that's the authentication type. I picked the wrong one. Let's go back to, is it this one? Yeah. Again, it's principal is star, so anybody can use the function URL to invoke my Lambda. And without that policy, it wouldn't, you wouldn't be able to, the URL would return essentially kind of a 404. So that's the resource-based policy. We might see resource-based policy again later on when we start looking at other services and getting those other services to trigger our Lambda. I'm just going to undo some stuff here. And also switch branches. Okay, so that's some of the IAM side of Lambda. Something I would have mentioned about the Lambda service way back is that the Lambda service automatically takes care of scaling and load balancing. So in the image here, what I'm trying to illustrate is, so supposing we've got this Lambda function and doesn't matter what the event source is, but let's supposing there are two concurrent instances of the event targeting our particular Lambda. Now, what the Lambda service does not do is it doesn't kind of queue up those events and pass them to our Lambda function one by one. Instead, what it does is it creates two parallel or boot ups two parallel micro VM instances, loads each of those micro VMs with the same Lambda function, and then distributes the events to our two micro VMs. So it essentially kind of scales up on the micro VM side, it scales up to deal with the volume of events. And if the volume of events keeps increasing, and these are concurrent events now, then it simply keeps on scaling up the number of micro VMs that it needs to deal with the large volume of events that are occurring. Now that scaling up isn't infinite. The AWS people decided kind of arbitrarily that it would set an upper limit of 1,000, meaning that within any AWS account, you can never have more than 1,000 micro VMs running at the same time. Those micro VMs now don't have to be all running the same Lambda function. So it's just in total, you cannot have more than 1,000 micro VMs running within your account at the same time. So there is an upper limit to the level of scaling that's permitted. But you may not want to allow the Lambda servers to scale up to 1,000 for a particular Lambda. Okay, so what you can do is you can set what's called the reserve concurrency. This is just something that you would set, in our case, in the CDK code. And what the reserve concurrency, you set it to a number, and that then becomes the upper limit for a particular Lambda function. Which means that, let's suppose we set the reserve concurrency to 10 for a particular Lambda, and let's say, 15 concurrent instances of the sourced event occur, then for 5 of those events, what the Lambda service will do is it will return a throttling error response back to the client. And a throttling error essentially tells the client, that the Lambda service cannot deal with the volume of concurrent events that have occurred. A throttling event or a throttling response it's a standard HTTP kind of a status code. I'm mentioning it here. I think it's status code 429. So here I'm just saying, so depending on whether your Lambda invocation is using the synchronous integration or asynchronous integration. If it's a synchronous integration or synchronous invocation, then it's up to the client to deal with these 429 status code responses. Typically what it would do is it would do a retry, maybe delay for a short period of time and then retry it. For the asynchronous integration, it means that the Lambda service actually has to deal with the throttling response, and it also retries, but it retries, I think it retries 3 times, and it has a delay period between each one, and then eventually it gives up and it actually queues the invocation into a kind of an error queue that you can subsequently access. I can give you a simple illustration of this scaling up that I'm talking about up here. And so what I've done is I have a simple little use case where I've got 2 lambdas, and I've kind of called them the invoked lambda and the invoker lambda. And the idea when we look at the code is the invoker lambda, it's actually going to generate 10 events which are targeting the invoked lambda. And so that will closely enough simulate 10 concurrent events targeting the invoked lambda. And what we'll see is we'll see the Lambda service spinning up a number of micro VMs in parallel. We can't really control, sometimes it might be 4, sometimes it might be 5, it depends really. We can't control how many it scales up to at any particular point in time. We can put an upper limit on it, okay, but if it doesn't reach that upper limit, we can't really control how many parallel instances. So just in terms of the stack for this simple demo, my stack is simple really. I've just got 1 lambda, got a lambda here. I'm generating a URL for that lambda. I've got another lambda, and you can see I'm passing into the second lambda. I'm essentially passing in a reference to the first lambda so that it can actually invoke it. And I've got a URL for the second lambda as well. And that's my CDK stack. Here's the lambda function that kind of does the invoking. And you can see here, like I've got a for loop, and this is essentially how you can talk to the Lambda service from a Lambda function. Yeah, so that's how we get one Lambda to essentially trigger another one. Wouldn't worry too much about the code for this, but there it is anyway. And so that's fine. Now I've deployed this already. So what I want to do is I want to trigger this Lambda and then see what happens on the other Lambda with the other Lambda in terms of scaling and all of that kind of stuff. So I've deployed this beforehand. So if I go into the Lambda service, I'm in there already. And where am I? Yeah, I am. Yeah. Let's see. So there's the invoked Lambda. And the invoker Lambda is this one. And I can grab the URL first from here as well. Okay, so there's the URL. So if I just click on this now, that's going to generate a GET request to that URL. That's essentially going to trigger the invoker Lambda. And then we saw the invoker Lambda has that for loop. There's nothing of interest in the invoked Lambda, it just has a console log, and that's it. So if I now just trigger it, okay, that's the response back from the invoker, so that looks fine. If we now look at the log groups though, and if we find the log group for the invoked Lambda, which is this one. Now, what you may or may not know is that there is a log stream created for every micro VM that Lambda creates for a particular Lambda function. Now we can see that there are 1, 2, 3, 4, 5 log streams. And if you look at the timestamps on them, they're almost identically timestamped. So what this is telling us is that there were 5 micro VMs booted up by Lambda, by the Lambda service, to deal with the 10 concurrent events that were targeting the invoked Lambda, this Lambda here. And the Lambda service will distribute those 10 events across those 5 micro VMs. And, if we look at any one of them, they won't necessarily, it won't send 2 events to this one, 2 to this one, 2 and 2. And, it won't necessarily work that evenly. It may send 4 to this one, 1 to this one, 3, and so on and so forth. So we can't really control. That really depends on kind of network issues, etc., which we don't have any control over. But if we just look at any one of them, okay, so there's a lot going on here actually. So just by coincidence, this seemed to have got a lot of events. In a log stream, the part of the stream that's labeled init, that corresponds to the initialization code part of our Lambda function. Now, our Lambda doesn't have any initialization code, but we still see this in the stream. It's followed by a start, and we know that the start part of the stream represents the start of the execution of the Lambda handler function itself. And then there was one console log in the Lambda, and that represents the end of the execution of the Lambda. There's a report that's followed by another start. The second start represents a second event that was sent to this same micro VM. But because this micro VM has already executed its initialization part, It doesn't need to run it again. So that's why it goes straight from end, straight into uh, start. So it runs the event handler or the Lambda function again with the new event, and on it goes. There's a third execution. So it seemed to have got quite a number of the events just coincidentally. And, if we look at the second one, it's probably going to have slightly fewer. That has quite a lot of them as well, actually. Some of them must have very little. Yeah, there's actually none, even though it spun up this, seems to have spun up this micro VM, but it actually didn't pass any event to it. That actually happens, like it will actually spin up a number of, when it sees a large, a number of concurrent events, it kind of spins up, I think it's typically about five as a minimum, and then it starts load balancing the events across those micro VMs. So, arguably you could say the load balancing wasn't great in this case because it seemed to send most of the events to the first two micro VMs. But because there was so little processing going on in the function itself, there wasn't a lot to be lost. So some of the micro VMs it didn't seem to use at all, even though it spun it up, as in this one here. Let's just look at the last one for the heck of it. Where are we? Am I looking at the right ones? What's in this one? Oh no, sorry, that's the. No, I've kind of lost my way there. Anyway, okay, so uh, we've got some sort of sense anyway of this auto scaling and load balancing that's taken care of for us by Lambda. Okay, so even though we didn't do it now, that you can set this reserve concurrency property in your CDK code, and that controls the. I could have done it for this one. I think the minimum you can set it to is 2. So I could have done that, and then we would see that there would only be 2 log streams as opposed to the default, which is kind of 5. Now, where the reserve concurrency is useful, though, is kind of in real life situations. If in real life, let's supposing you had 3 separate applications all within an AWS account, and the specifics of the applications aren't important, but let's just say this application here has a load balancer, and at the back end there's a Lambda that uh, can be triggered from the load balancer. This application has an API gateway. It has a Lambda function as well linked to it. And let's supposing we've got a third application which has a Lambda that, let's say, it has its own URL, and we can trigger that from the console. So there are 3 separate applications, let's just say. But let's supposing that there are no reserve concurrencies now set for any of these. So what can happen then is you can have a situation where one application kind of dominates the other ones. So what I mean by that is, let's supposing there's a high volume of activity on this first application to the extent that it actually consumes that 1,000 limit that's associated with our AWS account. So we've now got 1,000 micro VMs being used by this application, which means that for the second and the third application, if any events are targeting those lambdas, then there's going to be a throttling error response sent back to the client. And that's probably not a good setup, really. What you'd like is for each of these applications to be able to process some events at least, maybe not be able to process as many as that are occurring, but at least every application is doing some processing, and they're not just returning throttling errors for everything. So the way you would handle that situation is you'd put a reserve concurrency on this Lambda up here, and maybe the other ones as well. But then at least if we've got this high volume of events occurring, then some of the events will be processed, some of them will return throttling errors, but at least these two applications down here now, they can also do some event handling as a result of the reserve concurrency being imposed on this one up here. The last thing I want to talk about is this idea of cold starts and provision concurrencies. If we deal with cold starts first, a cold start is where the micro VM executes its initialization code and the actual function itself. So I'm saying here that a cold start is the sequence is a source event happens, a new micro VM is created, the initialization code, the new instance, well, I should have probably put in here, if there's a new micro VM created, then the initialization code has to be executed, and then the function, I do say it, the function's initialization code runs, and then the handler itself runs. So that's what we call a cold start. With a warm start, the micro VM already exists and it's being reused. And in that case, the event can be processed. The initialization code doesn't need to run at all because the micro VM is being reused, which means that the initialization code was executed sometime earlier. So the initialization code is not executed, and then the actual function handler is executed. It's probably slightly lacking now in that slide. I should have been clearer on the warm start. And clearly a warm start from a latency point of view is quicker than a cold start because we don't have, in the cold start we've got this initialization code that has to execute, whereas it doesn't need to execute in the warm start. And that's really what we were looking at there a while ago. If I go back again to those log streams, let's go back to this one. So like what we would say is for this execution of my function, because it's preceded by the initialization part, then we would describe this execution as a cold start. Whereas for this execution of my function or my handler, because it's not immediately preceded by the initialization code, then this would be classified as a warm start. Yeah. And that's simply because the micro VM is being reused. Now, ideally, we'd like to minimize the number of cold starts associated with processing events. And one way we can do that is by setting what's called a provision concurrency. So there are two types of concurrency settings. There's the reserve concurrency and provision concurrency. And what the provision concurrency is essentially doing is it's telling the Lambda service to spin up a few micro VMs, even though there are no events that need processing. It's telling it to spin up a few micro VMs in anticipation, if you like, of events occurring. And as well as spinning up the micro VM, it will also execute the initialization code part of the Lambda, but it doesn't execute the actual Lambda function itself. Now, obviously, you're paying for these kind of pre-initialized micro VMs, but if latency is a really important issue, then it's beneficial to your end users, I guess. Right. So that's just some extra stuff about the Lambda service that's worth being aware of. Go back to my website. Let's see. Nearly out of time, but let's keep going for a little bit anyway. So I want to move into these slides next, which is dealing with the API Gateway service. So the objective here is that we want to be able to develop serverless web APIs. And we know what web APIs, you've done a lot of web API development in the uh, Web App Dev 2 module. So we want to be able to deploy those web APIs into a serverless kind of environment, which obviously means using Lambda and DynamoDB. But how do we actually make them into a kind of a web API? So to be sure, what do we mean by web API? Web API is where we've got some functionality, and we know now that the Lambda service can take care of this part here. But we'd like a unified interface to all of this functionality. And the idea is that there would be multiple Lambdas here, but they're part of the same application. We want a single client-facing interface to all of these Lambdas. So how do we create this part? And the answer in AWS anyway. And how do we create it in a serverless kind of model? And the answer to that is we use a service called API Gateway. It's another kind of way of looking at it. Any kind of serverless application, what this screenshot is telling us is that any serverless application is made up of either logic components, state management components, or communication components. Now, by logic, we know that the service that we can use is the Lambda service. There are other ones like Fargate. State management, for example, we can use DynamoDB. We could also use S3 or RDS, which would be a relational database equivalent of DynamoDB. So we've got some familiarity with that. And then on the communication side, we've got a range of services, and we look at a number of them through this module. But right now, what we're interested in is API Gateway. And what API Gateway is it's fully managed service, and we know that that's a byword for serverless. And it's a fully managed or serverless service for creating, publishing, monitoring, and maintaining REST or just standard HTTP APIs. The difference between them is, that there are more features in a REST API from API Gateway's perspective anyway, than there is for a HTTP API. From a kind of user perspective, they look quite similar, but we will focus on REST APIs. And also API Gateway supports the WebSocket protocol, which we won't get to look at. And this is your classic kind of three-tier architecture, which I'm sure you're familiar with. So, you've got a client, could be anything, could be a mobile app, web app. Then we've got our backend, which in our case, we will implement using Lambda. There's probably some state management, which in our case will be DynamoDB. And then this is where API Gateway fits in the equation. It's the interface between our backend and our client. So how do we create API Gateway instances and how do we configure them? Is what we're interested in. Now, this API Gateway service, it has lots of aspects to it, most of which we won't get to look at. We'll just do the standard configuration. But if we just quickly go down through them, you can have multiple versions of a web API active at the same time. And it's kind of natural that a web API might evolve, like you add new endpoints to your API, or you change um, uh, maybe you remove some endpoints, modify them, etc. But because some of your clients may be programmed against the old version, we'd still like to make the old version available to old clients. So either way, we'd like to be able to run multiple versions of our web API at the same time. An API gateway allows us to do that. Similarly, during development, we'd like to be able to have different environments for our web API, whatever you want to call the environments. They don't have to be dev, test, prod, QA, staging. The names don't really matter, but at least to have different environments supported for a particular web API, and the gateway service allows that. Obviously, there's lots in relation to security. You can get API gateway to generate API keys if API keys are appropriate for your web API. And you can associate policies with those keys. Policies might be, for example, you might have limits on how many requests are accepted from the user of a particular API key. So you put some sort of upper limits and in terms of the rate of requests that it can send to your web API. And equally, if it exceeds those limits, then you return a trot, or API gateway will return a throttling error. Uh, API gateway understands Swagger and OpenAPI, those uh, web API specification standards. Supports WebSockets, as I said, and lots of other stuff as well. Now, if I go back to here, right? So API gateway, and then we have the backend that the gateway is integrated with. Now, it turns out that the backend, there can be lots of different options there. It doesn't have to be a Lambda, but the nature of the backend that determines the nature of the integration between your web API and your backend. So API Gateway supports a number of integration models, and that's what I'm talking about here. So there are four integration models. One is mainly used for testing purposes, really, which is called the mock integration. And that obviously would be useful if you actually don't have the backend developed, but you do have the web API interface. You're in the process of developing that, and you want to see that your web API interface is functioning properly. So you would integrate it with a mock backend, and the mock backend configuration would tend to return kind of standard default responses so that you can test your web API, but there's no real functionality as such. The second type of integration, it's given a number of names. It's called HTTP/AWS. It's also called AWS Services. Now, where this type of integration is used is when your backend is something other than Lambda. In the image here, I'm saying, for example, if you've got an SQS as the backend, and so the idea now is client sends a request, API Gateway takes that request, and presumably the request has a payload. API Gateway takes that request and it has to send the payload and maybe some wrapper information about the request and uh, send that to an SQS queue. Now, how does API Gateway kind of transform the HTTP request into something that's suitable for an SQS queue? And that transformation has to be described, if you like, to API Gateway. And we describe it using what are called mapping templates. These are typically written in YAML form. Fortunately, now we won't have to play around with them because they are quite kind of verbose to write and error prone. But the general point anyway is that this type of integration, HTTP, AWS, where it kind of gets its name from is you're going from the HTTP protocol into a protocol that's kind of internal AWS standard. Yeah. Uh, so you have to, and it's not just for SQS now. It could be S3, could be SNS, could be SMS or SES, sorry, for simple email service. So there are lots of different options here. And so you have to somehow explain to API Gateway how it transforms the HTTP request into a form that can be sent to the relevant backend. And as I said, you do that by means of these mapping templates that you attach to your web API configuration. So that's integration type 2, integration type 3, which is the one that we're interested in, and it's called either AWS proxy or Lambda proxy. And that's when you've got a Lambda here at the back end. And so now your HTTP request has to be put in a form that can be sent to a Lambda function. And we know that the Lambda function expects the first argument of the Lambda function is this event object. So the event object essentially has to contain all of the information about the HTTP request in terms of the payload, the HTTP headers, any query string parameters, all of that has to be packaged inside the event object that's given to your Lambda function. And API Gateway knows how to do that without you having to describe it by means of a template. Okay, which is kind of fortunate, really, because if we had to write templates for this, it wouldn't be much fun, really. So when we set this integration type, then essentially API Gateway kind of knows what to do in order to transform do the transformation both inwards and outwards, because the response that comes back from the Lambda is going to be a JSON structure, and that needs to be converted into some sort of HTTP compliant response. Now, I think I'm kind of running out of time. Yeah, okay. So I'll pick it up from there the next day. Now, as usual, there is a lab that's related to API Gateway. And essentially what we do in the lab is we take the same kind of lambdas that we had in the previous lab and DynamoDB. So, it's about getting movies and getting movie casts. We take those lambdas and we stick an API gateway or a web API in front of them so that they become part of one overall application. And because of the way these labs are written, you could work your way through it and see how far you can get. But we need to, in Thursday's lecture, I cover this stuff kind of formally. But there's no harm in being ahead of me if you wish. Okay, that's it for today. So I'll touch base with you on Thursday. Bye bye.